Okay, Chemistry 102 students, let's start talking about carboxylic acids and carboxylic acid derivatives. So in this video, I plan on just talking about carboxylic acids and getting started with those, and in a subsequent video, we'll talk about carboxylic acid derivatives. So let's get started here. Functional group formulas. So a carboxylic acid consists of a carboxyl group. So you can see that I have two different types of carboxylic acids represented here. One is an aromatic carboxylic acid and the other one is an aliphatic carboxylic acid. Both of them contain this piece that's highlighted in pink. And that part, if you remember from the functional groups that we studied way back in chapter 10, that is called the carboxyl group. So oftentimes you'll see that they're called a carboxyl group. Anyhow, so you should be aware of what a carboxyl group here, or what a carboxyl group means. And then you see AR, which represents aromatic, and R, which represents aliphatic. Now, for aromatic, the most common aromatic piece that we see in Chemistry 102 would be a benzene ring, or a derivative of a benzene ring. There are many types of aromatic compounds, but usually we're going to talk about some kind of benzene ring derivative. And anything that's aliphatic, that's any chain that contains carbons and hydrogens. It could be an alkane or an alkene or an alkyne. So down below here I have some examples of aliphatic and aromatic esters. So not only should you be aware of the carboxylic acid functional group, you should also be aware of the ester functional group. And the difference between a carboxylic acid and an ester is that whereas in a carboxylic acid, this oxygen here has a proton bound to it, but in an ester you have another carbon chain. And that carbon chain could be aliphatic, like this first one here, or it could be aromatic. So it will depend on the ester. But again, we'll save esters for another video. So the structure of a carboxylic acid. A carboxylic acid groups consist of two very polar functional groups. They have not only the carbonyl group, but they have a hydroxyl group. So if you look at this little picture of a carboxyl group here on the side, you can see that there's a dipole between carbon and oxygen because there's a difference in electronegativity there of about 1 unit, because carbon has a value of about 2.5 and oxygen is about 3.5. And I have another dipole moment going this way between this carbon and this oxygen. So overall, if I add those two vectors, I can see my net vector would be something like this. So that shows you that a carboxylic acid is a very polar, or carboxylic acids are very polar molecules. So you can see here these ball and stick diagrams here at the bottom. Again, the red atoms are the oxygens, the black are carbon, and the gray ones are hydrogens. And in this first molecule here, this is propanoic acid. You can see there's a dipole here between the carbon and oxygen, and there's another dipole here. What's nice about these models is that they give us more of a 3D representation of what's going on, and you can see that the molecular geometry here around this oxygen atom is bent. Anyhow, and then over here we have an ester. The name of this ester would be methyl acetate, and we'll worry about that later. But right now you can see there's a dipole here and a dipole here. Okay, so you can see that both carboxylic acids and esters contain two polar bonds between carbon and oxygen, but what makes carboxylic acids unique is that they have this bond here between an oxygen, let's see here, I'll get my green pen out here, between an oxygen and a hydrogen. So not only are carboxylic acids polar, but they have the capability to do hydrogen bonding because they have an oxygen-hydrogen bond that you can see here. So bonding, there we go. All right, let's move on. So physical properties of carboxylic acids. Well, if you have a low molar mass carboxylic acid, they have sharp, sour tastes, unpleasant aromas. A common carboxylic acid derivative that's used in organic chemistry labs is trifluoroacetic acid. So the formula for that would be CF3, and then you have your carbonyl, and then your hydroxyl here. So this is called trifluoroacetic acid. You don't need to have that memorized or anything. But this carboxylic acid, when you open a bottle of trifluoroacetic acid, which is sometimes abbreviated as TFA, it has such a high vapor pressure that it goes into the atmosphere immediately, and it will start to sting like your nose or make you feel like you have a sore throat. So they do have unpleasant aromas, and they can kind of, sting or get into your you know, anything in your body that's got moisture, so like your throat and your eyes and things that can kind of sting you. Anyhow, high molar mass carboxylic acids, if you've studied biology and biochemistry, I'm sure you've seen, you know, the classic biology where they show, you know, they say, okay, we have a carboxylic acid, and then they'll draw some kind of long tail like that. Well, that represents a fatty acid, and the reason we call it a fatty acid is obviously we have a carboxylic acid here on the end, so that's where the acid comes from here. But then this part down here is associated with the word fat, because fats are generally insoluble in water, and as you know, alkane, so this is a long sort of alkane portion of the molecule that would be insoluble in water. So low molar mass carboxylic acids are mostly what we're going to deal with in this chapter. They are water soluble due to their ability to hydrogen bond not only with water but with each other. So if you take a look at these little illustrations down here, you can see I have two carboxylic acids. So these are both acetic acid, and you can see here's my carboxyl group in one acetic acid molecule. Here's my oxygen, my hydrogen, and then here's another one down here. And I showed this in class one day, how a carboxylic acid can hydrogen bond with itself in two spots, kind of like this. And then over here, you can see this is another generic carboxylic acid. I'll just circle one of them in case you have a hard time seeing it. Oops, here we go. So there's one of them. So there's my carbonyl here. There's my bond to oxygen, there's my bond to hydrogen. And it's showing these carboxylic acids, they just have an R group here. You can see them hydrogen bonding with different water molecules. So you can see them hydrogen bonding with the oxygen here from the hydrogen over here. Anyhow, so not only can they hydrogen bond with each other, but they can also hydrogen bond with water, which renders them, of course, water soluble. Like dissolves like. So boiling points. What's the trend in boiling points for a carboxylic acid? So, due to carboxylic acids forming intermolecular hydrogen bonds, boiling points are at higher temperatures than those of any other functional group studied. So that kind of gives you a good rule to abide by for carboxylic acids in Chemistry 102. Whenever I give you any kind of question where you have to compare boiling points of two molecules of similar size with different functional groups. Let's say I want you to compare an alkane and an ether and an alcohol, just like I have here in the first line, then an aldehyde and a ketone, and then you see the analogous or a carboxylic acid of similar molar mass, and all of these have a molar mass around 60 grams per mole. It will always have the highest boiling point, and that's because of its ability to participate in so much hydrogen bonding. So I will probably ask some kind of question or some variation on something like this where I show a few different molecules and I ask you to rank them in order of boiling point. So of course butane only has London forces. Methoxyethane, an ether, has a dipole force. You can see that the aldehyde and the ketone, yes, they have a dipole, but the dipole is very strong. So those are going to have higher boiling points than the ether. And then you have the alcohol, which can participate in hydrogen bonding. But then, like I said, the carboxylic acid can hydrogen bond not only to the hydroxyl group here, but it can also participate in hydrogen bonding from the lone pair on the carbonyl carbon, which again renders the or gives the carboxylic acid the highest boiling point. So you should be aware of this trend in boiling points, and you can always guarantee that the carboxylic acid of approximately the same size will always have a higher boiling point. All right, so nomenclature. How do you name a carboxylic acid? Well, here's an example down here that I drew in by hand. You can see I have 1, 2, 3, 4 carbons. So the first thing you're going to do is you're going to find the longest carbon chain that contains the carboxyl group. So here's my carboxyl group. So I have that group. So I'm going to start. That obviously means that this carbon is going to have to be carbon number 1. I number them going from right to left. I replace E, so since I have 4 carbons, instead of butane, so what I'm going to do is I'm going to remove that E, so I'll erase that, and I replace it with oic acid. So butanoic acid is how you would pronounce that. So this is butanoic acid. And then complete the rest of the name, like it says, as usual. So I see that I have a bromo on the 3rd carbon, so I'm just going to add that to my name. So this is going to be 3 bromo butanoic acid. Butanoic acid. Good. There we go. Okay. So, carboxylic acid naming examples. I put this little structure in the top corner here, which has 1, 2, 3, 4, 5 carbons, just to show you the Greek lettering for common names. I'm going to talk about that in another slide. But right now, carboxylic acid naming examples. So this first carboxylic acid has 2 carbon atoms, 1, 2. If it has 2 carbons, think about it. If you have a 2-carbon alkane, it would be ethane. So we would call this, we drop the E, ethanoic acid. If you look at this second one here, it has 1, 2, 3 carbons. So 3-carbon alkane is propane. So we drop the E, it's propanoic acid. So you can see here, propanoic acid. Okay, and that 2-hydroxy, where do we get that from? Well, the hydroxy is on carbon number 2. The third example here is 3-methylbutanoic acid. We already covered butanoic acid, and I have a methyl group on the 3rd carbon, so 3-methylbutanoic acid. So these names below in the brackets, acetic acid, alpha-hydroxypropionic acid, and beta-methylbutyric acid, those are common names, and we'll talk about that in a second. Also, you should be aware of how to name dicarboxylic acids. So the way you name a dicarboxylic acid is your suffix will be dioic acid. So this one here would be hexane dioic acid. So you have a carboxyl group on carbon 1, and you have the carboxyl group on the other carbon, or excuse me, carbon 6. And then propane dioic acid, you have first a carboxyl group on carbon 1 and the other one on carbon 3, like that. And then these common names, I have a slide that shows those as well. So here we go, common names. So you have to know a few common names. So they use Latin or Greek prefixes, and the suffix instead of oic acid is ic acid. So if you remember, the IUPAC nomenclature used oic acid, but for common names we simply use ic acid. So Greek letters indicate the position of the substituent. So in IUPAC nomenclature we use 1, 2, 3, so on and so forth. But when we're dealing with common names, we use Greek letters to indicate those positions. And we've seen that before when we looked at the common names of aldehydes. Anyhow, so here we have beta-hydroxybutyric acid. So butyric acid, you just simply have to memorize that suffix in the beta-hydroxy. Since we have the carbon that comes after the carbonyl, that is always going to be the alpha carbon. So we have the hydroxy on the beta carbon, hence beta-hydroxybutyric acid. And then here we have the hydroxyl or the hydroxy group on the alpha carbon. So this is alpha hydroxy. We have 1, 2, 3 carbons total, propionic acid. So moving on to the next slide. If you look at the common names of carboxylic acids, what you have to be aware of in Chemistry 101 are the first 5 carboxylic acids. Okay, so you can see the IUPAC names are all given here in brackets. And those are a little bit easier to memorize because 1 carbon alkane is methane, so it goes methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid. But something that I'd put on the previous slide is a little bit misleading because it says for the common name you simply drop oic acid and then you put ic acid. Well, that's not entirely true because you have to remember the prefix as well. So the first one is formic acid. So when you have 1 carbon, that's formic acid. The second one is acetic acid. That's found in vinegar. Propionic acid, that's the acid that gives Swiss cheese sort of its tangy flavor. Butyric acid, if you've ever smelled the odor of vomit, which is, not very pleasant, that usually comes from, or that does come from butyric acid. And the last one is valeric acid. Just a little trick a student gave me a while ago. They said, okay, well, valeric has V, and V is the Roman numeral, equals number 5, so maybe you can remember that's 5 carbons. But the ones that seem to be the most challenging for students, I will say, in my experience, are propionic acid and butyric acid. So I'm going to circle those ones, or put a box around those. Again, you need to know the first 5. You don't have to know these. I'll just put here, not not required. You have to know the first 5, but the toughest thing is kind of setting out in your mind propanoic acid, propionic acid for common, and butanoic acid for IUPAC, and butyric acid for common. So again, you need to know the first 5. And if you practice them enough, they'll become abundantly clear. Also, if you remember back when we looked at nomenclature in Chapter 10, we talked about a few aromatic compounds, and we talked about benzoic acid and aniline and toluene and phenol. Well, you're going to have to need to know how to name a few benzoic acid derivatives. So by now you're already familiar with the structure of benzoic acid. Like I said, we've looked at it before. You should be aware that when you have a disubstituted benzoic acid derivative, you can use the ortho, meta, para nomenclature. So here we have a disubstituted carboxylic acid. It's metatoluic acid. If you have a methyl group as your substituent on a benzoic acid, you call it a toluic acid. So in this case, since the methyl group is 1, 2, 3 in the third position like this, we can call it metatoluic acid. Another name that would be acceptable for this molecule would be 3-methyl benzoic acid, but scientists love to use common names whenever they can. This next one here is ortho-bromobenzoic acid. Also, if you were to name this 2, if you named that 2-bromo-benzoic acid, that would be acceptable as well. Okay, so just as a refresher, if you remember, ortho is for 1,2 substitution, meta is for 1,3 substitution, and para is for 1,4 substitution, like that. So the last two examples are meta-iodobenzoic acid. I think that one's pretty self-explanatory. And this one here is kind of interesting. It's not, 1,2-dicarboxyl, nothing like that. It's actually got a common name, this 1,2-dicarboxyl benzene derivative. It's called phthalic acid. And you're like, well, why do I have to memorize that, or why should I know that? It's because it's used to make polymers and polymer derivatives. Anyhow, and there's another dibenzoic acid derivative called terephthalic acid that's going to come up either in the lab or in another lecture later on. So, carboxylic acids with phenyl as a substituent. So, remember that a phenyl group is benzene with one hydrogen removed. So, if you have, so the analogy would be if you have CH4, that's called methane, right? That's a methane. I think everybody knows that. If you see a CH3 as a group on a molecule, on an organic molecule, we call that a methyl group. Okay? And I think that everybody is aware of what the structure of benzene is. So this would be benzene. And if I remove, so you know that benzene has 1, 2, 3, 4, 5, 6 protons on it like that. If I remove one of those protons, I'm going to draw it in blue. If I take off one of those protons, okay, I'm just going to draw it down here for the sake of not having enough room, and I connect it to something else. When I look at this group as a substituent, I call it a phenyl. Okay, so methane, methyl, well, benzene and phenyl. I know they don't start with the same number, but that's how we name them. So here we have a carboxylic acid with 2 carbons here in this chain, so we have 1, 2, so that would be an ethanoic acid derivative, and we have a phenyl group on the second carbon, so we could call that 2-phenylethanoic acid. If you remember from the previous slide with the table that had the common names as well as the IUPAC names for carboxylic acid, you might remember that when you have 2 carbons in a carboxylic acid, that's called acetic acid, so we could call that, since this position would be the alpha position, we could call it alpha phenylacetic acid. And then this one here, I think if you understand this one here, then it kind of stands to reason that this would be 3-phenylpropanoic acid. Similarly, the common name down here, again, this would be the alpha carbon here. That would render this the beta carbon. So we have this group as a substituent. So it would be beta-phenylpropionic acid. Again, the common name propionic acid. IUPAC is propanoic acid. So common dicarboxylic acids, you can see that I put a little note here in red on the side. I think it's a good idea to have these memorized for the second exam. So in order, they are oxalic acid, malonic acid, succinic acid, glutaric acid, and adipic acid. I don't have any kind of acronym or anything or way of describing the acronym which I use, which is OMSGA. And then you know that since the common these dicarboxylic acids, the first one has to have 2 carbons. So as we go here, we have 2 carbons. Here we have 1, 2, 3, and then 1, 2, 3, 4, so on and so forth. There's just, you have to memorize them. So the first one is ethane dioic acid would be the IUPAC name. propane dioic acid, butane dioic acid, pentane dioic acid, hexane dioic acid, which is kind of a tongue twister. So these common names are a lot, easier to say. Oxalic, malonic, succinic, glutaric, and adipic acid. And you might recognize some of these from biology class, and we'll talk about those in another class. So some important carboxylic acids. More complex carboxylic acids are found in a variety of foods. So you've probably heard of citric acid before. That's found in lemons and limes and oranges. So it's found in all kinds of citrus fruits, citric acid. So that's a carboxylic acid. Also, you may have heard of lactic acid before. It's found in yogurts and cheeses and many other dairy products, and it builds up in your muscles after you've done some kind of intense exercise. Also, tartaric acid is another carboxylic acid. It can react with a carbonate in baking powder to produce carbon dioxide, and that makes the dough rise when you're baking bread. Also, another interesting point here, malic acid gives the sour taste to green apples. Also, again, fatty acids. I know those are kind of ubiquitous in biology. They come up over and over and over. Those are long-chain carboxylic acids found in plant and animal sources. And we'll talk about fatty acids quite a bit in this class later on. But again, the fatty acid just has the polar head group, and then it will have a long tail. And that tail usually possesses an even number of carbons, and that will be important later on in the class. All right, carboxylic acids found in food. So here are some of the ones that I just mentioned on the previous slide. But what's important, you don't have to memorize the structure of these carboxylic acids at all, but you can see that citric acid, here's a carboxyl group, here's a carboxyl group, here's one in lactic acid, there's two in tartaric acid, and there's two in malic acid. Also, I should point out that whenever you see the condensed structure written like RCOOH, it's the same thing as saying RCO2H. It's just condensing it further, okay? And if you were to draw it as a Lewis structure, it would be the same thing as drawing this. So all three of these mean the exact same thing. They're just different ways of representing the same thing. They're all identical. Reactions involving carboxylic acids. There's all kinds of interesting reactions that you can do with carboxylic acids. So they can be prepared by oxidation of a primary alcohol or an aldehyde using some kind of oxidizing agent. Now, the oxidizing agents that come up a lot in this class are potassium permanganate in a base or chromic acid. Either one could work for this. So you can take a primary alcohol, and you can clearly see that going from the primary alcohol to the aldehyde is oxidation, because not only are we losing hydrogen atoms, you can see that we lost 2 hydrogen atoms overall, but we're not gaining an oxygen atom, but we are gaining an extra bond to an oxygen atom. And then as you go from an aldehyde to a carboxylic acid, you're not losing hydrogens, but you are gaining an extra oxygen atom. So again, for our class, we're going to say that oxidation is gaining oxygen, losing hydrogen, and that reduction will be the opposite of that. So here we go. Carboxylate anion formation. Carboxylic acids behave as acids because when they dissolve in water, they will deprotonate or dissociate to form a carboxylate ion and the hydronium ion. So carboxylic acids, even though they're acids, they are not strong acids. Normally, if you just ask a general chemistry student, name me an acid, they'll pick a strong acid like hydrochloric acid or sulfuric acid. Those are very strong acids. If you compare the strength of let's say, acetic acid with sulfuric acid, the difference in strength between H2SO4, I'm going to write this down, between H2SO4, okay, is stronger than acetic acid. And that would be by about a difference of 10 to the power of 14. So that's more than 1 billion times stronger. So you were like, okay, well, if it's so much stronger, why do we still call it an acid? Because the definition of an acid, according to Bronsted-Lowry theory, is that an acid is something that donates a proton in solution. So we can assume that for carboxylic acids, they are weak and they only dissociate about 5%, and that is why we draw equilibrium arrows, because they only partially dissociate. We don't draw an arrow in one direction because that would be incorrect. We know this is an equilibrium process. So when you see the carboxylic acid get deprotonated, you could put in the lone pairs here. What you have here is the carboxylate. So you should be able to recognize a carboxylate, and I'm sure that everybody knows what a hydronium is by now. Okay. Neutralization reactions. Carboxylic acids do react with strong bases to form carboxylate salts. So this is called a neutralization reaction. If you remember from Chemistry 101, you would have learned that an acid plus a base gives you a salt and water. So an acid proton will be removed from the OH on the carboxylic acid to form water and a carboxylate. So let's go through this carefully here. So the carboxylic acid, the acidic proton in a carboxylic acid is always this proton. Okay, it's the proton that's bound to the carboxyl group. So that's our acidic proton. So I'll put here acidic like this. So here's an example where it's reacting with a strong base, sodium hydroxide. The hydroxide is taking this proton over here. So it's actually pulling this proton off of the carboxylic acid. So of course when I combine this OH with this other H, I'm going to get H2O. That makes sense. Okay. So where's my carboxylate? Well, I formed a carboxylate. Okay. So if I just look at this in itself, I see a carboxylate, just like in the last slide. Okay. If you look at the carboxylate anion right here, here's our carboxylate. But in the next slide, it shows a counterion. Okay. So let's take a look at it here. Let's go back. And the counterion here is sodium. So sodium plus, because here overall the charge of our reactants is 0 and the charge of our products has to balance out as well. So we call that, when we see the carboxylate solvated by a cation, we call that a carboxylic acid salt. And what do we know about salts? Salts are made from a metal, like sodium, and a non-metal, and organic molecules are made completely from non-metals. So this is an ionic compound. So this is going to be a very, very soluble compound, a carboxylic acid salt. All right, acid-base reaction. So here's just a couple of examples. So if you take a carboxylic acid like ethanoic acid or benzoic acid, and you treat them with a strong base like sodium hydroxide, you end up with a carboxylate salt. So I can put here carboxylate salts. So these are going to be solids because they're ionic compounds. And of course you end up with water. And this color coding here is just to show you that the water molecule is formed from the blue OH and the red H. Where are they? Here's the blue OH, comes from our base, and then this is the acidic proton, and again this is the acidic proton. So how do you name the salt of a carboxylic acid? First you're going to start by naming the cation. So naming a cation is very simple. So it could be, for example, sodium, or it could be lithium or potassium, etc., etc., etc. Then you're going to drop oic acid. So if you had sodium benzoate, let's say, that would look like this. So you have, everybody knows by now that this would be benzoic acid, right? This would be benzoic acid. So if I just erase that hydrogen, okay, like that, I'm going to have my carboxylate. So instead of benzoic acid, it would be benzoate. I replace oic acid with ate, and then I just name my cation. So in this case it's sodium, so it would be sodium benzoate. So there's all kinds of uses for the salts of carboxylic acid. Sodium benzoate is actually used as a preservative in soft drinks, and soaps are made from carboxylate salts as well. So in the next video we're going to talk about esterification, which is when a carboxylic acid reacts with an alcohol to form an ester and water.